Okay, so good afternoon, and I was was just saying that okay, we showed it this morning this renormalization, and let me summarize the discussion by writing down final equation. We will give rise to our a priori estimate. Okay, so this is the key point. Once you have the estimate, then essentially most of the work is done. So let me go through the material of this morning. I don't just to copy. Yeah, so we tested and we got this equation. Wait, let me see. Okay, this is not the final one because we defined psi. Okay, that was the final equation actually. So let me bring it with the. Okay, so this is the estimate from this morning. So I will recall later what are all these terms. Actually, let me just summarize also that here you can integrate by parts, or do I do want? Yeah, let me do it now so this is actually, you can write as nabla epsilon square. Actually, it's a vector, so maybe we want to write in this way, and then plus m square psi square. Okay, so this is this quadratic part. And yeah, and then we had all this, the non-dangerous term and then the dangerous term. So let me go back to pick up how they look like after we finally had, okay, these were the terms. And okay, so we were in this situation. So we had this dangerous term and we replaced them. Yeah, sorry. So we replace them with all these terms. So let me just write down everything. We will not really look into the detail into every terms, but just to summarize them in one single place. So I replaced this this orange part with these two lines plus plus this last line. And you add that. Okay, and maybe I got the sign wrong, but somehow it's not very important at this point of the discussion. So let me just ignore maybe the problem. I leave you as an exercise to check the sign. Okay, so here we are. So we replace this line by all these other lines, and we got this equation. Okay? So right hand side and left hand side. Sorry. Okay, then let me recall also. So where, let me summarize all the terms. So where we have so we have a bunch of terms. So y1 is just y. Y1 is y. Yeah, let me. Yeah, let me summarize the regularity. So I just register the space regularity. Okay, so y1 is like, let me maybe make a table because otherwise. Sorry. So y1 is like this. Then what we had y2. I just register all the term we had. So these are the objects we constructed along the way. So you see y2 of regularity -1. This is y2 minus a constant, which we call c epsilon. And then we had y3, which was like the cube and 3 times the same constant times epsilon. And this was in 3/2, but somehow let us recall that this is not very precise. I don't know how to write it. Let me. Sorry. Yeah, okay. Let me write in this way, in the sense that it's not very precise, okay? but in first approximation we had. Then we had H. Let me copy where I have H somewhere. Yeah, here. And what else? We had this new object, so I copy also them. So we have this, and then we have like 2, 3, 2, 2. But so here it's the same, but with the Laplace, with the parabolic operator. And here is the different, yeah, constant d, and then we have 2, 3, or 3, maybe 3, 2. No, sorry, it was 2, 3. And we have like something like this, okay? And then regularities where, so this object has regularity. So maybe let me put the regularity on this other side. I'm not sure how to organize this. This was in this is here, this is essentially there, this is in 1/2. Now let's guess where they are. So this was like -1, this gain 2. So this is in 0 minus. This is also in 0 minus, and this is in minus 1/2. Okay. And finally, I just recall what is the relation between, you see psi and phi, and then we have to recall what is the relation between the two, and then we're done. Yeah, the relation is here. Yeah, let me copy. Okay, let me just copy these 2 lines. Okay, let's call it. Okay. Okay, finally, everything, yeah, it does not stain. Let's see if I can make it in one screen. Yeah, hardly so. So these are the data for this afternoon. Yeah, maybe let me try to just organize in 2 columns. Maybe it's better and it's more proper. Put it here. Yeah, it looks better. Okay, so we have all this data. Okay, and whatever, it's not very important. Okay, so what is the message from this morning? So the message is we had these good terms, and then we have a bunch of somehow bad terms in the sense that they don't have a sign. And as in infinite volume and as in the 2-dimensional case, now the goal is to try to use the good terms, which are the terms for which we have control. So let me just mention this last line, I put it there, but just to remove very soon, because the point of this last line is, did I miss? No, exactly that this last line tells us that these 2 constants are this. So essentially this last line you can write in this way, okay, minus plus, or if I got it the sign right. Okay, so we can choose, so this last line can be removed because you just made this equal 0, okay? And we chose then beta essentially, okay? So we can ignore this last line essentially. And we have to control all these other terms, and we have these commutators. You see, we have essentially three commutators, one here, one there, and the other here. And then we have all terms, but they are quite nice. Okay, for example, look at this one. So the we said that this is a regularity 0 minus, and phi. What is phi? Let's go back. So phi can be read out here. So it's almost of regularity 1. Okay, so this will be like will be living in some space like H1 minus kappa. Okay, if you want. Okay, let me say let me add things. Let me add this information maybe here, just to, so phi will belong to, essentially that's the idea of this estimate. Phi will belong to that, and psi will belong to H1. Okay, so we added this decomposition. So okay, you see the estimate for psi is written here. Okay, this is H1. We have the control of the H1 norm of psi. And for phi, you see it here. Okay, phi is equal to, okay, it's equal here, but here is not very nice because you want to exploit cancellation between these terms. So you have to read it here is H1, and then you have this object, and this object has regularity is better. It's 1 minus kappa, but in this infinite integrability space. Okay, remember these are like this space, but where the integrability index is infinity. Okay, and this is living in H1 by the a priori estimates. Okay, meaning this is B1 to 2. But okay, we don't care very much. Okay, the point is that the regularity is enough. Okay, so in the a priori estimate, so let me remove now all this material which we don't need anymore. Yeah, that's, I don't know. Okay. Okay, so this is the situation. Okay, we have a bunch of terms. These are these y's, which we can control somewhere. Series of probabilistic objects of explicit. This one, let me remember. Yeah, this is not very useful here. So let me just. And they are known. So phi, yeah, okay, so we have essentially one unknown, but you could consider it just a system which is just satisfying the decomposition. If we want, there is only one unknown actually, is x. Okay, so what you're doing here, it's that you define other variables. So psi is defined like this, and then phi is defined like this, and psi is defined like that, and then the a priori estimate tells you that you have these regularities for these different objects. Okay, so you have, okay, you can put also h here. This is -1r minus kappa. If you want really to put all the unknown, implicitly there is also this one, even if it disappears from the question. But you see, you still have z. So let me write z. In the equation, we still have z. So we still have to track z, and z regularity is 1r minus kappa. But even better, because for, yeah. Where is z? Remember, z is x minus. So where z is equal to x minus y1. Psi is that, okay, whatever, just relation between the various objects, okay? So z is defined like this, and psi is defined like that, and it's equal to that, because psi is defined like this. Okay, anyway. And okay, you can check by yourself that somehow the regularities on the right hand side are all nice. Of course, I didn't told you exactly what these commutators are, but you can start to see that somehow you have -1, -1. Okay, in this commutator there is also some there is some linear operator going on. So you have to check how they are defined, and you will see that they gain regularity actually. So trust me that I don't want to go into the details. Maybe it's not very useful right now. But all these terms essentially on the right hand side can be controlled with the term on the left hand side. So let's call yeah, so okay, with this decomposition, one is able to prove that. Let's give a name at the right hand side. Okay, so the left hand side is equal to something. Let's call it is equal to something. Let's call it A, where A is defined like this. Okay. Prove that the right hand side can be estimated. There exists an explicit polynomial function Q. Okay, then explicit function. One could compute, okay, but it's not Q or Y, such that you can estimate the right hand side with Q or Y, which depend on Y, plus the right hand side, okay, plus a small quantity or small delta positive. There exists whatever, such that you can put here something like this. Okay, so this is like into the mesh. Okay, at this point, this kind of argument proceed as in d equal to via functional analytic estimates. Okay, you just have to estimate things. Now every term. So let me go back. Every term in the right hand side, for example, this term can be estimated like some norm of psi to equal to, like this dip psi y, sorry, and some norm of like the L1 norm or some Sobolev norm of this, and then you have to check that you can do for every term. This term is not there anymore, and all the other terms, they're fine, and they can be estimated in this way. The function Q of Y depends only on Y. And what is Y? Y is the set of all these terms. So Y is just, you just put all these terms together. Okay, I don't have, let me write them down because I don't have really a notation for them right now. Then you have H, but H can be estimated in terms of Y. So I don't put H. Okay, so trust me that if you have this equation, you can solve this equation in terms of Y, and you can estimate H in terms of Y. Okay, that's so the only thing you have to have some control, probabilistic control, are these terms. And that's somehow the philosophy of these approaches, is that you somehow use analysis to arrive at a point where all you have to know about the probabilistic objects is somehow summarized in a finite number of terms. So let me call them Y, via norms of the kind. And then this polynomial depend only on this, but only via the usual norms, like continuous function from 0t, if you do it in an interval, like in C minus 1/2 kappa, and so forth. Okay, so this kind of norm, of course, for every for example, for phi 2, the right norms, okay? For actually depend only on y3, it depends on what you can make it depend only on this. And yeah, let me write in my summary. This term you never need, okay? You see that there is no y3 in the formula, there is only in the expression of h, there is y3 here. So actually you need only that one. And this is how it's defined, is the L1 minus 1 of this object. And this is now really in, so this is good. So it's a continuous function of time, and then it lives like in 1/2. So that's a better way to, to express these objects. And when I say this, of course, these functions do not have any notion of smoothness. Okay, recall that we are on the lattice. We are just saying that you can have uniform estimate in these spaces, which do not blow up as epsilon go to 0. Okay, meaning that we can have uniform estimates in the corresponding spaces which do not blow up as epsilon go to 0. Okay, and then we have the unknown. Okay, so, and you have this thing, and Q depends only on these norms, okay? So Q of epsilon, it's really a function of these norms, okay? It's not, it's a polynomial function of these norms. Okay, so this is under control, okay? In particular, Q of epsilon, the supremum. Okay, you can, for example, you can have something like this, okay? This is finite, okay? The supremum is finite, but actually you can have more, you can have that it's finite for any power if you really need it. Okay, so you can take power and, sorry, the power inside, because outside does not make. Okay, so you have this uniformity, and that's the key, okay, at this point. Using this, so this is like, I don't know, estimate 1, okay, using this estimate. So using this in the a priori estimate, so here, so using in this a priori estimate, yeah, here I didn't put any, yeah, let me just write it differently maybe. So that I can put an equation there. Okay, so now I can put an equation. And like this is key equation. It's not very nice, but okay. So if we use 3, so the estimate of A in terms of Q of Y and these good terms in 1, we get that for delta small enough. Okay, you can take 1/2, you can take something. Now you have an estimate of this kind, okay? So these are the good guys, you lose a bit. So let's say you use 1 minus delta. Yeah, of everything here. This is smaller or equal of Q of Y, something like this. And that's the point now. Okay, so that's now the real. That's now the real estimate. Okay, so here, if you want, this is like a theorem. Okay. Okay, so this is really, at this point, we are in the same situation, provided beta is chosen depending on epsilon in a precise divergent way. Particular, there will be, beta will be like C, some constant. Yeah, I don't. So it will look like C1 epsilon minus 1 plus C2, and C1, C2 depend on lambda, okay, something like this. Then you have logarithmic of epsilon minus 1, okay, with constants C1, C2, which we computed above. Okay, so provided you select this value of beta or something which is asymptotic to this value of beta, then there is no other diverging term in the equation, and you have this equation. Okay, and of course the right hand side depends on epsilon this way, so you have, of course, also the solution depends on epsilon. Okay, I'm ignoring this fact, but as in Dute mentioned at this point, as in d equal 2, this can be now used to obtain a priori estimates for the measure, okay? By taking the average. Okay, so this is now, is like in 2 dimension. Okay, you take the average and use stationarity. So I'm skipping and putting, so I'm ignoring actually some technical problem which need to be addressed. In particular, one cannot construct stationary solutions to the equation for H. Okay, so these I ignore, but let's say so let me put stationarity. Okay, so let me put this as a remark. In the paper there are all the detail, and how I don't want to enter. There is a small problem in the sense that you cannot really solve for H in a way that you get a stationary process. Okay, so as a consequence, so since, let's go back. Okay, so the question for H cannot be solved in a stationary way somehow, because you see you have to solve a parabolic equation, but somehow there is no, it's not obvious how to solve it in a stationary way. So in the paper we don't find a stationary process. So these processes can be constructed in a stationary way, because Y is stationary and these are just a function at a given time. These processes also can be constructed in a stationary way, but this process is more complicated. Somehow you see it's not a finite, in particular, it's not a finite polynomial, okay? Because if you start to do a Picard iteration, every time you multiply by y squared, you increase the degree of the polynomial. So this cannot be seen as a finite polynomial, and you cannot solve in a stationary way. For this reason, everything which depends on H, so X is stationary, Y is stationary, that's no problem, but everything else, in particular psi and phi, are not stationary anymore, because you subtracted something which is not stationary. Okay, so as a consequence, both both phi and psi are not stationary. And the argument to get the appropriate estimates in average has to be modified. Okay, so just a small warning, in the paper it's written, so here now I ignore it unless you complain and you want to see the details. Because, so remember what we did in two dimension. In two dimension, we just took the average, and somehow here we had something which is stationary, and we were done, okay? Because the average here was finite, the average here gives the estimates we want, okay? This is positive. So we are controlling a positive quantity above with a quantity we know well, and we are done. In this case, you cannot cancel this, and you have to deal with it in another way, and it can be done. It's not difficult, but it will add like another maybe 15 minutes of explanation how to do it. I want to ignore, okay? But the changes are minor. Okay, one ignores this point. Yeah. Anyway, one obtain at the end that, okay, you get an estimate like this, okay? The expectation of that is bounded by the expectation of that, which then, which gives, yeah, let me be precise, because now, since they are not stationary, I want to be precise. So now you obtain that, yeah, you obtain that for any t in a given interval, you have this estimate, okay? Relation with of psi and phi with x allows to obtain tightness. That is, one can prove that. Now, of course, these are not the variable we want, okay? These are auxiliary tools which allows us to control what we want, but what we want is to control, for example, x, okay, and y, okay? And here what you will obtain is that you obtain like estimates like this, okay? That any power of this guy, let's put epsilon to understand that depend on epsilon, so that this is bounded, okay, for example. And remember that we are on the torus, so this is like T3 epsilon, okay? And even better, with some more care, one can prove that, yeah, so for any p positive, and even better, one can prove even like better estimate. Not the regularity, you cannot hope more than that, okay? That's the point. But somehow to estimate x, you estimate the decomposition, and then at some point you have to estimate phi and psi, and then you have to use these a priori estimates. And actually, with some more care, one can prove that it's even better than that. One can control a quantity like this, okay? For small k positive and beta positive. Okay, so this means one can control not only the integrability, the power integrability of this norm, but somehow you know that this random variable has, remember that this is stationary, okay? So you can Let me write like this, at time 0. Maybe I don't, maybe put epsilon there. Okay, so I mean, this is the time. Okay. So this is this is essentially the supremum over epsilon of the integral. Let me write back. So you know something about the measure. Okay, this is, let's go back to our measure. This is nu epsilon. Okay, so you know this kind of estimate for the measure. Okay. So the measure nu epsilon allows uniform exponential integrability for some power less than 1 of the norm of this norm. Okay, we are not able to get power 1. It should be possible, but not with the technique we use, and so you have this norm. Okay. Okay, this somehow solved the problem, okay, because this gives a tightness, okay. This is more than enough to obtain tightness. And actually, let me remark, okay, let me, I will make more remark about this tightness because that's not our final objective, okay. Let me say the 543 measure. Okay, so now this is not still the final goal, okay? We have something to do. And this something to do is put things together, okay? We have to put together, we must now put together the epsilon to 0 proof with the let's say like this, okay, proof. Combine better. Okay, and this is actually quite easy. Okay, it's false what I'm going to say. I said it's easy, but you have, so let me say this is not difficult, but one needs to pay attention to some subtle detail. Okay, so let us start by noting that the above a priori estimate works also with weights. Okay, so yeah, one can, instead of testing with, so remember at some point we tested the equation, testing the elaborated equation with phi, one test with rho phi, okay, like rho square phi for some polynomial weight rho, okay. This make appear norms, weighted norms, okay. Sobolev norm, Bezov norm of the type. Let's see, so what will appear is that somehow, I mean, we did into them, sorry, like we did the infinite volume limit, Okay, so these norms are like this. And somehow what are going to appear something like this, that is, there will be some weights around like this with some exponent, okay? And also, and then you will have like norms like phi with some exponent, that will be like 1/2 L to the 4. So these are the kind of norm you will see appearing instead of, and this will be on the full torus, okay? So now you have lambda, epsilon, or m. Okay, now you want to consider the full torus. Okay, so this is in the full space. Then there will be norm like this. There will be like some H1 norm, which one can write like this with the weight outside, and the weight here it's 1. And okay, so all the objects you see there, they have corresponding like weighted norms around. Okay, so sigma positive, and also norms like for the solution. Okay, and then one can conclude. So now the point is that the first point is to make sure that like norms like this, okay, are uniformly bounded in M as M goes to infinity. Okay, so now the problem is this, okay, is how we check the regularity. Regularity is fine, but what happens to the stochastic process in the full space, okay? And the idea is that all the processes yt, so let me write yt where t is just the generic index. Grow at infinity at most polynomially with a small power. Okay, in particular, one can prove things like this. Okay, I can prove, for example, that y1, when you take the literal Paley blocks, because it's a distribution and you compute, let's say, at a given time and in a given point in space, this is now a nice random variable, and this can be bounded by a constant time a very small polynomial of x. Let's delta, I don't know. So in x is growing not very fast, and this is the constant is random, okay? And also in time is not growing very fast, okay? So you can bound it like this, okay? For any time, it's stationary. For any point in space, uniformly in, okay? Actually, you don't put, okay? Uniformly in M. Okay, let's just write it. Uniformly in M and epsilon, okay? For some finite random constant G. And this constant is actually somehow these weighted norms, for example, okay? So this is the kind of estimates you have, okay? You don't have better estimates than this, okay? It's clear, it is somehow clear that one cannot get better estimates. In particular, this kind of stochastic processes cannot be bounded in the full space without weight. Okay, so I give you an example. So just to understand what is the problem, okay? Let me give an example. Maybe you know, but if you don't know, take just a family. Let's call, okay, let me give a different name of GN, a family of ED Gaussian normal, okay? Standard normal random variable, because this is a model, discrete model, okay? So my claim is this random variable, you cannot expect a Gaussian stochastic process or something which is driven by a Gaussian stochastic process to be bounded in the full space. So when you look in the full space, you will see very large fluctuations, okay? And the best bound you can get somehow are, yeah, okay, maybe, no, yeah, let not me give the example. Okay, so the best bound you can get, so you can prove something like this, for example, for a family of independent Gaussian, then one can prove that there exists a random constant such that so Gn is bounded by the constant 1 plus log n to the power 1 alpha, I think, something like this. And this is true then for any, almost surely. Finite, okay, almost surely. Such that then you have this behavior, okay? So let's put probabilities. I think you can even, yeah, you can even just make only the constant depend. I think it's like something like this, okay? And here you have a deterministic cost, okay? Or some deterministic constant, okay? So this is the kind of behavior you have to expect from random fits, okay? That especially if they are Gaussian, they at most grow logarithmically in the space variable. Okay? And how you prove this? Okay, one prove to prove this. One shows that, for example, this is one way to show is that you consider this random variable. You take the sum over the Gn squared with a sum. Okay. So you take this random variable, like, is integrable for small beta, okay? This implies that it is finite, almost surely, okay, because it's integrable. And then, of course, that each that, okay, then one has, for example, here, of course, you have that every element of the sum, it has to be smaller than like this n square the full sum. Okay, that's clear because this depends on omega, so everything depends. Okay. But okay, what happens here? This implies now if I did okay, let me do this computation for you. So you take the log, then you have 2 log n plus the logarithm of the constant. And then you divide by beta, so you have beta. Sorry, I don't want to divide this by beta. And then you take the square root. So you get an estimate for the square root. Okay, so you have something like this, and you can, of course, always then bound above by something which kind of I wrote here. Yeah. And this is for all n. Okay, so you have this kind of idea which has to be used to estimate the growth of this kind of processes, but it's quite standard. And Okay, so where is the problem? So this is not a problem. Okay, you introduce a weight, and as we did in the infinite volume limit, you have weighted estimates. Okay, you have to be careful because unfortunately this equation poses problem. So let me write it again. So this equation is a bit problematic in its limit. The biggest problem come from the equation of H. Recall. So you have to solve this equation in the full space, okay? Since it cannot be solved easily, it cannot be solved in weighted space, okay? So linear equation is very difficult to solve in weighted spaces, okay? Because imagine that, is it clear to you why? So we said every y is growing at infinity, okay? This is not a problem of regularity, it's a problem of the growth at infinity of this object. So every y is growing, so you have to imagine also that h is growing, okay? Because it cannot be smaller than y cubed, for example, okay? But then if h is growing and h2 is growing, but this term is growing faster, okay? And then you cannot close the estimate, okay? Because indeed, so indeed the loss of, indeed there is a loss of, okay, weighted weight in the estimate of the second term. I don't know how to say it, okay? But if you try, you see very fast what is the problem, okay? If you multiply, you see, if you try to close this equation and you say, okay, I multiply with a weight, you multiply with a weight here, it's linear, so you don't have much choice, okay? You can multiply with a weight, and here the weight, now you have to decide, do I give the weight to y square or h? And you have to give to h because you want an estimate for this quantity, so you have to put the weight here. Okay, you can make so that the weight is associated to h. And then you are lost because this object grows at infinity and there is no weight which can help you, okay? So there is a problem with this estimate and one need a trick. One can then use a trick to solve this problem. See the paper, okay? I don't, but I just mentioned the problem. It's not very interesting if you are not willing to work with this kind of problem, okay? It's a technique which somehow we found, which it's very nice, but it's a technical problem. So let's stop to discuss the infinite volume limit. Essentially what I'm saying right now is that actually most of the work has been done. When we discussed the infinite volume limit, understood how to use the weight, and when we discussed the ultraviolet limit and understood what are the terms one has to control. And then one has just to check that when it tests with the weight and you get a bunch of terms and you can always estimate them with putting powers of the weight somewhere, okay? Okay. And one obtain estimate. Let me write down the estimate with the way they looks like this. Okay, so at the end of the day, one obtain, for example, estimates like this. Let me, at the end, one obtains estimate form. And now you are in the full space. Okay, so this is like lambda epsilon, and you have a weight here. Okay, something like this. And they are uniform in epsilon and m. Okay. this. So this is an important moment because this is the kind of estimate. Okay, this is enough, well enough to have full tightness, both in the epsilon going to 0 and in the m going to infinity limit, irrespective of the size of lambda. Okay, so lambda can be large, okay, can be arbitrary. So in this sense, somehow this is a fully non-perturbative technique, okay? You don't need any assumption on the size of the perturbation to prove this result. Okay, so this is somehow a key point because from here you prove the existence of the limit. So let me maybe be precise and reintroduce M now. Here there is no M because somehow you can extend periodically, but somehow it's the measure which depends on M. Okay, but the space, as I told you, you can take the full space and just periodic function you extend periodically so that you work in the same space. Yeah, so in conclusion, one obtain accumulation points of the family, okay, epsilon m, and then it is easy to prove that any of these accumulation point is translation invariant and reflection positive, okay. Moreover, the estimate, so this estimate which I wrote here, which I call, let's say, exponential estimate, allow to prove the technical condition required by the Osterwalder-Schrader reconstruction. Okay, so this is important to have this. One has to work a bit to have this exponential integrability, but this is important to have Osterwalder-Schrader reconstruction. So any limit point nu give rise to, okay, to an Euclidean, to a translation invariant, no rotation so far, reflection positive, and nice measure, okay. And then to a quantum field theory, okay. So the by Osterwalder-Schrader reconstruction. Okay, so that's the goal, okay. So we proved that there is this family of measures which depend on two parameters because you have the mass and you have the lambda at a variable, okay. We don't have uniqueness. We do not have uniqueness nor rotation invariance, okay. If you can prove uniqueness, if one can prove uniqueness, it should be easy, okay, to prove rotation invariance. In some model, you can prove rotation invariance, but then you don't have translation invariance, okay? So you have to give up something at the level of the regularization, and then it's difficult to get it back, okay? So you prefer to have translation instead of rotations because translation somehow give rise to the energy and to the momentum operators of the theory. Anyway, you need translation in the time direction to have a ground state for the quantum theory. Okay, so this is the end, if you want. Okay, so we constructed the object. There is no uniqueness, so there could be more than one. There are various points still to be addressed. but maybe I make a small pause to ask you if you want to ask questions. So now what I want to do in the last hour is just discuss some properties of this measure. Okay. So maybe let's make a pause and see if we want to discuss something else more in detail instead of going into a new subject. Okay, it's not new, but different aspects of this measure. Okay, I just want to I don't know if I want to write. Yeah, so well, we proved our initial theorem. Okay, if you want, we proved that there exists. The only thing it remains to prove that the limit is not Gaussian. Okay, it would be very deceiving if after all this work we end up with all the accumulation points that we can find that they are Gaussian. Okay, so one has to check this. And we do it in the paper. Maybe I want to discuss about this right now, but first, let me ask you, do you have questions, remarks, comments? You want me to explain better some parts which I skipped over instead of going into a new direction? Okay, does not seem okay. So I think you can ask because I imagine I was a bit fast, so maybe everybody's lost at this point. So I'm not sure if I want to go on with the new subject, or if you want me to give more detail on something I said in this last few days. Let me think. So let me yeah, there is some question here in the chat. Okay, so the proof of non-Gaussianity, yeah, so I think we can look at this. I find this very interesting. So, okay, let's now prove some properties of this measure. So let's actually, maybe I can even ask a subsection, okay, property of 543, some properties. First of all, that for any lambda, different from 0, of course, any accumulation point is non-Gaussian. So that's not what you want, okay? Ideally, one would like to have non-triviality. Yeah, that the corresponding quantum theory describes interacting particles. Okay, so that's what one wants. So a Gaussian measure is trivial. So let me put this as a remark. So just to make the difference between these two things, okay? Because in probabilistic language, you could say trivial to say Gaussian, but in this context, there is another meaning to the word triviality. So triviality means that you have a theory where you see particles coming from infinity, converging in a given region and going away undisturbed. Okay, so these particles do not see each other. And okay, I didn't discuss what are particles, but somehow intuitively you could imagine that at CERN you've very well seen that particle interact. Okay, so the theory underlying elementary particle is non-trivial. Okay, you have really interaction. And if you understand a bit also what happens to C waves, okay, you have two waves which come from very far, and then they arrive in the same region and they have to interact because they move the same water. Okay, and of course in the approximation where the waves if you are in an harmonic approximation, then these waves do not interact. Okay, but the point is that you can have non-harmonic effect in the oscillation, and then you see interaction and they go away, but they have different directions. So it's like a collision. Okay, and of course you have integrable system which they looks interacting, but actually they contains excitation which do not interact. Okay, so Litonic excitation. So it's not obvious to see a theory and say it's interacting or it's not. Okay, you have really to prove that what is called the scattering matrix is non-trivial. Okay, that is, you have a probability that what you get out is not positive probability, that what you see in the future is not what you have introduced in the past, for example. Okay.
Okay, sorry. So can I have a question, right?
Yeah, sure.
So you say that, okay, we will just prove that it's non-Gaussian, but we will not prove at the moment that it's not.
No, I don't even understand the proofs of non-triviality. So it's complicated because you have to, there exists proof. So people proved in the 70s, 80s that when you construct 543 with other methods, then you can prove that the quantum theory is non-trivial. But the proof it's not so easy, and I don't think in the paper we don't do it because it's complicated. It was not the point of the paper, and it's not done in many ways. Okay, there is maybe one of two papers which do it, or even one only, and it's really, I mean, I'm a probabilist. I want to understand better, but at this point I don't really understand all the subtlety and what you have really to do to prove non-triviality. So you have to reconstruct the correlation function of the Minkowski theory. Okay, so you cannot work in the Euclidean to see non-triviality. And this means that somehow you need to have more control. So Osterwalder-Schrader reconstruction alone is not enough. You need more information to be able also to transfer other Euclidean information in the Minkowski space, because it's non-triviality is really a question of the particles of the theory. And you don't see the particle in the Euclidean setting. Okay, there is no waves, there is no propagation. You don't see the particle. Everything is encoded very implicitly in the Euclidean theory. You see, so you have to like make Euclidean continue. You have to, have a more detailed study of the correlation function, which at the moment we don't have. Okay, so I just prove, first step is to prove that it's not Gaussian, okay? Because if it's Gaussian, it's trivial, okay?
Okay, thanks.
This is not done. But I mean, there are not many papers that do it, okay? It's not something which is easy to do, and even in 2 dimension, it requires some work, okay? And very precise knowledge of the Euclidean theory. So my hope is that at some point, one gain, even with the stochastic approach, one gain enough control that he can do that. But you see, at the moment, we are very far from that, okay? We don't even know, I don't understand very well how to prove uniqueness easily for like high temperature without using, of course, you can always use a mix of techniques, okay? But somehow my goal is to try to use only this kind of ideas, okay? If I'm allowed to use maybe correlation inequalities because the measure has correlation inequalities, then maybe you can do something. But I think for me now the intellectual research is to understand better the methods, and you understand better the method if you try to prove difficult things with this method. So uniqueness is still an open problem. When you have uniqueness, maybe rotation invariance, it's easy. But okay, so let's see how we can understand, because you see, I have accumulation points. You don't know very much, okay? We have these estimates at the moment. So let's prove that is non-Gaussian, okay? So this is the first point. And I find interesting because somehow gives some information which usually is not available in the other approaches. And we have to go back and see what are so this is the description we have, okay, of the theory. So we have to go back to this description. So we have to go back. So what does it mean to prove? So let us call nu an arbitrary accumulation point. Okay, so the first idea, the first remark to make is that one can actually, so somehow from this approach, you have to understand that, so all the work we made is not just we constructed the measure nu, or we construct a measure nu, is that this measure is coming with a lot of structure because we have all our decomposition. So if we are careful and we track all these quantities through the tightness argument, then one has more structure to work with, so that one can actually prove tightness for the tripole. So you just don't want, so of processes, of stationary processes. So you have, okay, we just, so the measure nu is just the value, the law of x at a given time. And that's, you have tightness. But if you look what we did, we can prove that x converge as a process, y converge as a process, and actually y cube converge as a process, okay? And you can add also the other, but let me see if it's interesting. I think I don't need the others. But you could try to track all the other processes in the limit, and that's yeah. No, actually, I need only these three, okay? I will show you, okay, for the tripole. So imagine that they depend on epsilon m, okay? So everything here depends on epsilon m because they are processes. Okay, let us call. And now I call x. Okay, I just track them through this, and I take a limit point and I call them an accumulation point, okay? A possible limit, okay? Possible, a limiting law of the family, okay? Of this family here. Okay, so you have, of course, x0 is distributed like nu, okay? Okay, of course, it's not unique, but what I mean here is an accumulation point for nu epsilon, okay? That's, of course, the law at a given time is, but you have more, okay? But we have more. Also, the dynamics and a coupling of x and y. Okay, so that's, we don't have only x, we have a coupling between x and y. Okay, we have the law, we have the joint law. Okay, in particular, this coupling satisfy the same estimates as we had before the limit. Okay, so we have this information that is, so let me go back. So what we had before the limit, you see that you have x, y, and then h, but h is essentially, yeah, I'm not sure if I want to use h. So let me see. So in H, there is this irregular part, and then there is something which is a bit more regular. So what essentially I can prove that when I pass to the limit, let me see if it's should be enough. Let me just check before writing down something that is not. Yeah, sorry, let me check this. Non-Gaussianity, I need to check what I really need. Yeah, so we had something like this. Okay, so I can show. So this we have this coupling in the limit. Okay, so now we are in the limit in the continuous space, the continuum time, and we have these three processes. And essentially, sorry, let me carry not that one, but carry that because it's more useful. And now we know that if you subtract here lambda, yeah, I don't remember what you have to subtract. What is h? H is minus lambda over 2 that, okay, and in first approximation. So you subtract that. So now we are in the limit. And what it says is that this difference has some regularity, which you can check here before the limit, and then it passes to the limit. So what is the regularity? Essentially, the next term is this one. This is -1, and this is 1. So this is of regularity 1 minus. Okay, so we know that this minus this plus this as regularity is in like H1 minus kappa. Okay. So we have this information, okay? This information will allow us to, in particular, we have, so let me be a bit, I'm skipping some technical detail under the rug. But so what you have is that now if you take the Little-Pali blocks, okay, of these three guys, then this object is of size 2 to the I minus, it's of positive regularity, okay, so minus 1 plus k, okay. Okay, so this is the information we have on the measure, okay, which you don't read only from nu, because nu is telling you something only of nu 0. And this is telling something that you can construct a coupling where, let me interpret this, okay, so this estimate tells us that there exists a coupling between the interacting field x and the free field y, so that x is in first approximation given as above. Here, so what does it mean in first approximation? So in this very precise, okay, in this very precise sense that if I look at high momenta, then at the interacting field, no, at high momenta, so xi at high momenta, then I see essentially the free field and then a correction coming from the interaction. So this is like first order imperturbation theory. And then something else whose size is well controlled. Okay, so this is how I want to interpret this estimate. Okay, telling you this interacting field is the free field plus the first order correction in perturbation theory plus something else, which are all the other non-perturbative contribution. Okay, so you see this is validating perturbation theory, but this is not perturbation theory because lambda is arbitrary. Okay, can be very large. This says to you, if you fix lambda, then you look very high, very large, so very high momenta, then you see essentially perturbation theory. Okay, so this is an expression of asymptotic freedom. Okay, in the ultraviolet. So if you of the theory. Okay, I would like, I think, yeah, I think this is the right way to express it. Okay, so now in the ultraviolet, what you're seeing is the free field and then the perturbative theory of the free field. Okay, and this is what is asymptotic freedom. That is, if you look at the renormalization group in the ultraviolet, then you converge to the free theory. Okay, and this is the key for showing Gaussianity. Okay, now in order to show that X, so what I want to show that X0 is not Gaussian. So how you prove that something is not Gaussian? Well, you prove a contradiction with the hypothesis that it's Gaussian, and the easiest thing to do is to compute the fourth moment and show that it's not the fourth moment of a Gaussian. Okay, one can show that the fourth moment is not given by the usual formula for Gaussian. Okay, yeah, one look. Okay, so we look at, so what you can look, well, you take the average of the blocks. So I take the blocks at time 0 and in a given point. Okay, so we look at the 4-point. So if you speak the language of physicists, that's a 4-point function. Okay, and you subtract the connected parts. So you have to subtract like 3 times. You have to think what's going on if it's Gaussian. So it looks like this. Okay, if you do it for a Gaussian, you will get like, yeah, these are 4 legs, and then you need all the ways you contract this with the others, and this is 3, and then you have other 2. So maybe I did it wrong. This is 6. Somebody let me, are you better? Yeah, because okay, here I took 4 different points. I think in the paper no, sorry, because you choose 2 and then you don't have choice. Yeah, I wrote it well. So for the Gaussian, for a normal Gaussian, the 4 moment is 3. Okay, because of this reason. So you subtract 3 times the covariance. Okay, let me give a name. So this is like U4, whatever. You define U4 of XXX like this. Okay, so it's a 4 linear function of X. Okay, so we look at the 4-point function. Okay, we want to prove that U4 is different from 0. Okay, this implies, because it implies that X is non-Gaussian. No, that, okay, I mean, this, if you do it for Y, you get 0, okay? Because Y, it's Gaussian. You can check yourself. Y is Gaussian. So now you see the strategy, okay? So now, moreover, U4 is a multilinear function. So we can use our decomposition of x to write. So now we use our decomposition. Let's give a name to this difference. Let's call it, I don't know, I need a new name, zeta. No, I don't like zeta. Yeah, let's call it zeta. Okay, so you write x is equal to y1 plus, sorry, it's not plus, it's like minus lambda y3 plus zeta. Okay. And now you write u4. Okay, so y1 is y. Okay, just don't get confused. So now you write this multilinear function. Okay, so what you get? Well, you get all the terms are y, or one of them is y3, and it's not very important where I put. So actually, I have 4 of these contributions. So actually, I have twice that. And then you have other terms. So sorry, yeah. And then I have other contributions. Okay. Like when 2 are y3, or yeah, I don't care very much of the coefficients of this other contribution. Okay, plus things like this. Okay, and okay, you have all the others. You get the message. Okay, and you have also something like there are different constants. Okay, you have something where you have z, or when more than one z, etc. Okay, so you have a lot of contribution, but you don't care, because the point is that this is 0, and now you want to estimate how large is this. An explicit computation shows that this object is as large as it can be. Okay, so how large is this? Okay, remember you took the blocks, so actually this depends on the blocks. Okay, so it's like UI. I could have taken different blocks, just this is the easiest thing that works. Okay, so every piece in the block, so this behaves like, this is of the size delta E y to the power 3, and then like, okay, size, it has this size, and you can check that actually it behaves like this quantity. Okay, and what is the size of this object is 2 to the I, and then you have to compute this, and when you compute an average instead of estimating the size, this is really 1/2. There is no k loss. Okay, so you have 1/2. So every of these objects is of size give you a contribution So every of these objects give you a contribution of size 2 to the I. Sorry, I'm starting to get lost, but essentially this gives you a contribution 3. Yeah, okay. And what happens here, this gives a contribution of size. Okay, you have to really to compute this quantity, because you don't want an upper bound, you want a lower bound, but essentially that's what you will get. Okay, you get exactly, sorry, this is growing, and this is not growing. So how it was going, this was, sorry, was not like this, was -3/2, but you gain, so you have -1/2. So overall you have 3 of this guy like this, and then you have -1/2, and this is exactly 1. Okay, so you have this. So this quantity you can compute, and it's of this size. Okay, what upper and lower bounds. Okay, so you have this, And now you have to check what happens to the other, okay? But so that and rough bounds show that. So what happens for this one, for example? Let's see the one which has 2, okay? You see that here this object goes like, now you have different, for the first 2 you have like, now here you estimate, so you lose from, like Borel can tell you, so there will be like something like this. You have one of these for every power of I, and then you have the positive ones for the powers of k. Okay, they are going to 0. Okay, these are becoming very small because they were regular. So now you see that you see these 2 power balance these other 2 power, and this essentially is of size 2 to the I to the power whatever, some power, let's say. Sorry, this is plus here and this is plus, so you have like 4 kappa. Okay, so this is much small. Kappa is very small. Okay, so this is much smaller than that. Okay, and all the other terms are as small and cannot compensate for this term. Okay, so finally one deduce. But I find the computation, it's not very difficult, but I find very interesting this computation because you really see that somehow the correlation function in the ultraviolet, they behave like the free theory plus perturbation theory, at least first order perturbation theory. Okay, so this behave like this, you know now that this is exactly this, that plus quantity which has small of 1 to the I. Okay. Actually, you can be, you can, they are even smaller than that, I think. So that's the proof, okay? The only difficult part is to do the computation, the exact computation, but yeah, you can get, yeah, I wanted to see if I can give you an exact estimate. I think the most difficult estimate are with Z. You need to do, but I think at most they grow at as let's say order of 2 to the I. Yeah, the other contribution are a bit larger because the estimates for Z are not so good. So you get 1/2 plus 5k, something like this. I don't know. Okay, but it's not very important. Okay, anyway, it's much smaller than 2 to the I. Of course, if lambda is different from 0, okay, which is different from 0 if for I large enough and lambda different from 0, okay, of course. So this proves non-Gaussianity. Okay, and actually shows that the correlation function in the ultraviolet are given by perturbation theory, by first order perturbation theory. Okay, I'm not very precise, okay, but yeah, okay. Which I find very interesting. So somehow it's a fully non-perturbative situation, but there is some region of the phase space where the perturbation theory works, but this is not what you expect from the standard idea that the coupling is small. Okay, here the coupling can be very large, but the point is that when you look at high energy, it's becoming irrelevant. So it's like if it was very small. Okay? Because somehow the contribution are the Gaussian contribution is very large. not that the interaction is small. It's that the Gaussian contribution is very large and the contribution of the interaction are not as large. Okay, so I find very interesting this phenomenon. Anyway, okay. Yeah, that's, I don't think I have time to discuss. I wanted to discuss Schwinger-Dyson equation, but I think it's very late and the course has been very long for everybody. So I want to stop here. So now I proved what I wanted to prove, that is the existence of this measure and some property. So now we saw many of the property. We spent a lot of time discussing reflection positivity and the meaning, even if I didn't define it for you on the lattice. But this is an exercise, it's not very difficult, just requires some notation. And what else? And then we we both learned how to use, so I hoped to have shown to you that, yeah, using stochastic quantization, one can derive constructive results. Okay, so let me maybe wrap up from the course. So, to finish. Up. So my main goal in this course was to show you present several topics. So, and let's list them. So, so the basic conceptual structure of quantum mechanics and the link with probability theory via the Euclidean approach. The meaning of certain of reflection positivity as the bridge between the Minkowski, between quantum mechanics and the Euclidean quantum mechanics and quantum field theory, or quantum field theory and the Euclidean quantum field theory. Okay. And then, so how stochastic quantization via Langevin equation allows to describe, to study certain measures, certain difficult as push forward of easy measures. So how to control the infinite volume limit via PD arguments involving weighted spaces, and how to control the ultraviolet limit via via paraproducts and paracontrol decompositions. Okay? That is decomposition involving paraproducts. Let me write, and decompositions involving paraproducts. And last but not least, how divergences can be extracted and matched with counter terms with local counter terms in the interaction. Okay, what is called in the bare interaction. And then finally, how the resulting measure can be analyzed via the decomposition obtained and the coupling with the free theory. So you see, they are different, okay? So let me so somehow you have this coupling, but despite the fact that 543 singular with respect is not absolutely with respect to the free field. So that's maybe an important point which looks technical for you, but somehow you see the measure of x, so the law of x is not absolutely continuous with the law y, but somehow in this point of view, you don't see this difficulty because you see, okay, x is still y plus other things. Okay? So you have this coupling, which does not, I never saw in other approaches, and I find very interesting that you can construct this coupling. So somehow there is a possibility to describe the interacting theory using a free theory in a very precise sense, in a pathwise way, not in a perturbative approach. Okay, so I stop here. I think the course finished here. So the end. Let me. What I want to write some center. Oh, the end. Okay, and let me stop recording.